Just a note, we're doing chapter 24 a little bit early. There's some chapters like probability and binomial probability distribution function, which the book has before this chapter. We're doing this chapter first because it's super important for IAs, and the others are not so much. So sometimes I'm going to have to give you some information about the probability chapter or binomial distribution chapter early. Okay, so in this first paragraph, we're talking about chapter 23, which we haven't done yet. In chapter 23, we had a random variable, and the random variable could take on different values, but they were all integers, 0, 1, 2, 3, etc. So I'm going to put those here because the binomial probability distribution function could take on values between 0, 1, 2, 3, all the way up to a small n value, where small n was from the set of natural numbers. Okay, so basically small x could be any one of these integer values. For a continuous random variable, also called big X, the values it can take on, small x, can be any real value. So any decimal value. In this case, the probability can be defined by a probability density function instead of a probability distribution function. They are similar in that if you find the total area of this function, it adds up to 1 in the same way that the individual probabilities in our probability distribution functions adds up to 1. Let me show you an example of what we're talking about here. So a binomial probability distribution function looks something like a little bar graph or histogram. Each one of these numbers, 0, 1, 2, or 3, has some chance of happening, and we represent that chance of happening with these little bars. So like the chance of 0 happening, let's say it's like 0.2, the probability of 1 happening is like 0.3, the probability of 2 happening is 0.4. So do you see like each one of these integers, whole numbers, has a probability represented by these little rectangles, right? What if you actually can have any decimal value occurring? Then you make kind of like a normal distribution function or any kind of density function, which is like, it's like a curve instead of like these little rectangles. And basically to find the probability of some value happening, you actually define an interval. Like, let's say if I want 2 to happen, then maybe I'll do like, oh, I'm going to look at the area between 1.5 and 2.5, and I'm going to color that in, and I'm going to figure out what is the percentage of this area relative to the whole area. And of course the whole area is 100% or 1. Okay, so in general it doesn't have to be a normal distribution function. It can have any shape. So we call that in general a probability distribution function, not necessarily a normal one. So here we're talking about the general probability distribution functions. If the probability distribution function has some shape and it goes from left interval or left boundary A to right boundary B, then we know that if we integrate the area from A to B of the probability density function, we should get a total value of 1. The probability that the random variable x lies in the interval C to D, and so that would be like some kind of subset here, C to D, for example, is the integral from C to D of the probability distribution function. Okay. It might seem strange at first, but in the continuous random variable case, the probability that random variable x can equal exactly a particular value is 0. What do I mean by that? Notice that here, to figure out if the probability was close to 2, we're going to integrate from 1.5 to 2.5. Then we're going to get a significant area here, right? But what if we wanted to figure out the probability that it was exactly 3? Then we would try to integrate the area directly above 3. And remember that if you integrate from 3 to 3, the probability density function, you're going to get 0, right? Because the area between a number and itself is 0. So kind of weird to think about, but that is true. So the probability of random variable x equaling a specific value of x is always going to be 0. For this reason, what we can say about these expressions, probability that random variable x is between c, d, the probability, oh, and look, notice that this one has less than or equal to. Notice this one has less than or equal to, but this one does not. Notice that this one does not, and this one does. Are these different? No, they're all the same. Okay, because remember, the probability that it's exactly C or exactly D is 0. So just if you include, like in this case, I included C and D in the interval, it doesn't make it any bigger than when you have C and D not including the interval. So all these expressions are equivalent for a probability density function. 24a, normal distribution. Okay, give 3 examples from your life of variables which have normal distribution. We've talked about this a lot, right? So I could say height, weight, IQ, SAT scores, etc. Write the probability density function for the normal distribution. Okay, I'm going to write that down. I'll be back in a second. Okay, here it is. Looks crazy, doesn't it? We're going to talk more about this later, but you've seen this function before, even though you probably don't remember it. Basically, what is the difference between this function and a plain e to the negative x? E to the negative x, if you remember, is like a decaying exponential function. If you put a squared here, what it does is it reflects the e to the negative x kind of around the center axis, and it makes a normal distribution shaped thing. Okay, so that's the basic core of it. I'm going to point to the x squared here. I'm going to point to the e here. Everything else is kind of extra to make it the right size. Okay, and of course the minus mu centers this normal distribution function around the center mu, and the sigma widens it or narrows it. Okay, do you remember when we did transformations, we had f of b x minus c, something like that. So remember, the c does horizontal transformation, so that centers it around mu, right? And the b, if you remember, is like a horizontal compression. So the b is kind of like this sigma on the bottom, so it widens and narrows the normal distribution depending on how big your standard deviation is. Okay, let's move on. We write, so like whenever we want to indicate that we're using the normal distribution, we use this code, which is x tilde, and then we put n, and in the parentheses we put mean, which is mu, comma, and then the variance, which is sigma squared. What do I mean by variance? Variance is the standard deviation squared. Okay. Usually on the exam, if they use this notation just to remind you that this value is not sigma, it's sigma squared, they'll give it to you usually with a number squared, so then it's more obvious that the 3 is the sigma and it's not 9. Okay. The normal curve is centered about x equals mu, and as x approaches positive or negative infinity, the curve approaches the x-axis as an asymptote. So we saw that in this picture, right? So in the picture we can see it's centered at the mean, and then on either side it approaches the asymptote of the x-axis. The height of the normal curve at x equals mu is, so that's where this expression comes in. So this expression is the height of the normal distribution curve at the center. You can see how you can figure that out, because like the center value is mu, right? So if you put mu in for x, doesn't this whole fraction become 0? E to the 0 is 1. 1 times this crazy looking fraction at the beginning is of course the crazy looking fraction. So the height of the normal curve at x equals mu at the center is 1 over sigma square root of 2 pi. Okay. Describe the shape of the normal curve. Bell shaped, right? by differentiating this normal curve once, then twice, we know that the maximum of the function is at mu, and the inflections points are at, it turns out that the inflection points of a normal distribution, remember the normal distribution, it has like 6 sections that we can kind of see. The place where concave down becomes concave up turns out to be right here and here, and these are the two values that are separated from the middle value of mu by 1 sigma, because remember each one of these sections is 1 sigma. So this one here is x minus mu, or I'm sorry, mu minus x, mu minus sigma, sorry, mu minus sigma, and this one here is mu plus sigma. What percentage of values lie between mu minus sigma and mu plus sigma? Do you remember 68, 95, 99 from the investigation? So the middle two sections are 68%. So between mu minus sigma and mu plus sigma, it's 68%. Between mu minus 2 sigma and mu plus 2 sigma, it would be 95%. And between mu minus 3 sigma and mu plus 3 sigma, which is here and here, it would be 99%. So that, we get those values from 68, 95, 99 mnemonic. Okay, let's move on to the problem set here. And we're going to solve these problem sets, these problems here, using the 68, 95, 99 mnemonic. Now, if we know that the middle two sections are 68%, that means that this is 34% and this is 34%, right? And if the middle 4 sections are equal to 95%, that means that this is 13.5% and this is 13.5%. You can check for yourself. 13.5 plus 13.5 is 27. If you add that to 68, that gives you 95, right? That'll make this into 95. And then finally, if we add 2 more sections, each one of these 2 sections is 2% each, because then if we add 68 plus 27 plus 2 plus 2, that gives us 99. Okay? All right. So now with these percentages here, we can solve these problems. So it says, and we don't even need to use a calculator, state the probability that a randomly selected normally distributed value lies between sigma below the mean and sigma above the mean. So sigma below the mean and sigma above the mean would be from here to here, right? And so this would be the middle 68% section. So we don't even need to look at this diagram. We know that the middle 2 sections are 68%. So we'll put 68%. The mean and the value 2 sigma above the mean. So that would be the mean, and 2 sigma above the mean would be this section and this section, both of those sections. So it would be 34 plus 13.5, which would be 47.5%. Okay? All right, next section. The mean average rainfall of Cloudona for August is 48 millimeters with a standard deviation of 6 millimeters. Over a 20-year period, how many times would you expect there to be less than 42 millimeters of rainfall during August? So let's mark the mean and the standard deviation on our picture first. It's always good to draw a picture for a normal distribution problem. In this case, the mean is 48 and the standard deviation is 6. So in the middle, I'm going to put 48, and then to the right and to the left, I'm going to add and subtract 6. So that would be 54, and that would be 42. Okay. Over a 20-year period, how many times would you expect there to be less than 42 millimeters of rainfall? So less than 42. What a coincidence. It falls exactly on a standard deviation line. So if it falls exactly on a standard deviation line, we know that, this middle section is 68%, and this section here is 13.5, and this is 13.5, right? This is 2. By the way, if this is 2 and this is 13.5, what's remaining here? Well, if you do the subtraction, you'll find out that this remaining section here is what's left over from 99%, which is 0.5 on either end, right? 0.5 here, 0.5 here. So that means that these three sections together would be 13.5 plus 2 plus 0.5. It turns out to be 16% here. So the chance you would expect less than 42 millimeters of rainfall would be 16%. All right, that's it for the first page.